If you have the opportunity to tour around the Virginia Tech powerhouse or power plant, you really should do so for a couple of reasons. One is when you take the tour, you will find that there are more components within that power plant than just the four components comprising the basic Rankine cycle. The reason for that is that there's always an effort to improve the thermal efficiency of a power plant beyond just the basic Rankine cycle. There's another really neat thing going on with the entire Virginia Tech power and heating system that I need to cover in this section, and also give you some ideas behind what's going to be covered in the rest of this chapter 8. So we've covered the basic Rankine cycle, and so that means you're probably maybe 60 or 70% of the way through chapter 8. But there's some additional components that you may be assigned in your homework. And so that's what this is all about, to give you an introduction to those power plant components. And those additional power plant components, the purpose of those additional components is to improve the basic Rankine cycle thermal efficiency. And so there's a lot of slides in this section, but I'm going to try to blaze through them as quickly as I can, just to give you an introduction of what you're going to be exposed to in the rest of this chapter 8. So, of course, here's the review of our basic Rankine cycle. And you can, I hope now, you can identify those four basic components by heart without having to go to a cheat sheet. And I also hope that you could plop down a TS diagram that basically describes that cycle. As a reminder, remember that there are some built-in irreversibilities associated with the basic Rankine cycle, and I've tried to depict in this slide the heat transfer across a finite temperature difference. And so this image sort of depicts the real world, where in your boiler furnace, you've got to be operating at a temperature higher than T1 to get heat transfer up to T1. And similarly, in the condenser process, your cooling water or your low temperature reservoir has got to be some temperature below the condensing temperature of the steam. And so visually you see with those red arrows, heat transfer across a finite temperature difference. And that is a big source of irreversibility in the world. And so why would we want to improve power plant thermal efficiency? Why would we want to do that in the first place? For me, once I went out and got a job and found out the reason I was working, it smacks you in the face. So the thermal efficiency is the energy sought over the energy that costs. And so why are we trying to maximize this number? Well, what we're trying to do is increase our revenue as much as possible. W.net, the net output, if we can increase that just a little bit, we're going to get more revenue, okay? Or if we can decrease the cost it takes to operate, we're going to improve the thermal efficiency, and we're going to reduce our operating costs. We're going to save money. So my point here is that as an engineer working in this energy field, it's all about minimizing the cost to operate, minimizing that, and maximizing the value of the net power that you're selling or you're providing to your internal customer. It's as simple as that. Okay, now, so for the quick overview of where we're headed for the rest of this chapter, how will we reduce heat transfer across a finite temperature difference? And so there's three basic bullet items that I believe are going to mimic some of your homework assignments. One is called regeneration equipment. These would be called heaters, feed water heaters, two different types of feed water heaters. Another method for reducing heat transfer across a finite temperature difference is reheating the steam once it's gone through the first section of a turbine. And then finally, the third method for reducing heat transfer across a finite temperature difference is closing up the heat rejection temperature difference, closing up the difference between the cooling water temperature and the steam condensing temperature. So those are all associated with reducing heat transfer across finite delta T, source for irreversibility. The next one is recovering waste heat from high temperature heat source. In other words, look, in many cases, we have very high temperature exhaust gas leaving the exhaust stack. And as engineers, we try our best to recover heat that we can recover from that heat source. So that is another way. And what we typically do with that is we heat the feed water with that waste heat. Another and really powerful way, an innovative way to improve our thermal efficiency is what's called cogeneration. And I'm going to try to give you a little idea of what that buzzword is about and how it relates to Virginia Tech. Okay, so now some quick slides going through about regeneration. So regeneration is a fancy word for feed water heating. And what I want to do is introduce you to the idea of what's called an open feed water heater. This is a vessel. It is purely a cylindrical horizontal vessel. And here's what it does. It takes in pumped condensate from the condenser. So you've got a pump underneath the condenser, and it's pumping water into this vessel. At the same time, you're taking extraction steam from the steam turbine. So you're pulling away some mass flow, a fraction of the mass flow leaving the first section of a steam turbine, and you're mixing those two streams together. And that's why it's called an open feed water heater, OFWH, open feed water heater. That means that these two streams are mixing together, okay? And when you mix those together, basically, you get a saturated mixture in this horizontal vessel. And so below the operating line is going to be saturated liquid. Above this line is going to be saturated vapor, okay, just because of the nature of gravity. And so let's see, a little bit, that's what I want to cover there. I think I've got some other things to point out, but do recognize key points. Two streams coming in, basically liquid, compressed liquid coming in, and extraction steam coming in. This vessel is operating above atmospheric pressure. Vessel operating above atmospheric pressure, typically 10 to 30 pounds per square inch gauge. Okay, what's coming out of this vessel is saturated liquid because of the nature of gravity, and it's going on to the boiler feed water pump. Open feed water heater. Another really neat, a neat advantage to this open feed water heater that is higher than atmospheric pressure is that there is a purge vent, and it's a small pipe that simply goes up through the roof to the atmosphere. And what that does is that it takes a small stream of this saturated vapor, which may contain some dissolved oxygen. So let's say from the tap, right? If you're putting some tap water in to make up a stream, it releases oxygen from the saturated mixture, and that really helps the operation of the boiler because it's very bad to get oxygen in a very high temperature area. That would be rust on steel pipes. So this intimate mixing of the steam and water accelerates the release of dissolved oxygen in the H2O, and it simply goes out through the roof. The other kind of really neat thing for engineers is, you know darn well what's coming out the bottom of this open feed water heater tank. It's saturated liquid. No doubt about it. Saturated liquid is coming out the bottom of this tank. This is a great screenshot that I found off the internet. The manufacturer's name is called Cleaver Brooks. That's a company of an open feed water heater. This would be one of the biggest open feed water heaters I've ever seen. Look at this person standing on the ground relative to the size of this vessel. And so this is what a power plant scale open feed water heater looks like. Okay, just just huge. And so the arrows going in, that's going to be the inlet feed water, steam, and condensate returned from other heating sources that you may be using. A little bit more on that later. But the neat thing is what's coming out of the bottom of the tank is saturated liquid going off to the feed water pump. Advantages and disadvantages of the open feed water heater. Great advantages enables elimination of non-condensable gases like air or oxygen that's dissolved in the H2O. Very powerful tool. Also, this open feed water heater raises the feed water pump inlet enthalpy, and therefore the boiler inlet enthalpy, if you think about your pump analysis. And what that's going to do then is it reduces the early boiler heating load from having to heat that feed water up from a lower temperature. It starts out at a higher temperature, thus reduces the heat transfer across a finite delta T, and that's what ultimately raises the thermal efficiency of the power plant. Also, it reduces the feed water power requirement since you're coming into the feed water pump at a higher pressure than sub-atmospheric. Okay, disadvantages. It requires extraction steam from the turbine, so you're stealing a little steam away from future turbine sections. It requires the addition of a condensate pump underneath the hot well of the condenser. And so basically, any reduced feed water pump load is offset by the condensate pump load. That's kind of a disadvantage. Okay, that was what's called an open feed water heater, and the why. The why will you have a homework problem associated with an open feed water heater? I will help you with the calculations in a future video. Next type of regeneration. The next type of regeneration is called a closed feed water heater. So we're showing the sketch, and this is a classic shell and tube heat exchanger. And so typically in a closed feed water heater, the two streams do not mix with each other like the open feed water heater. So for example, the way this works is we're going to take extraction steam from the turbine coming in, typically the shell side of the heat exchanger. And so it's going to be hitting that hot steam is going to be hitting colder or warm feed water coming in. And so this extraction steam is going to be condensing. And because of gravity, what's going to be coming out of this bottom flanged connection is saturated liquid. So you're condensing your heating steam down to saturated liquid. And so therefore what you're doing is you're heating your feed water or condensate from an inlet temperature up to a hotter exit temperature. So this side is going to be purely liquid coming in and going out to the feed water pump. This side, the shell side, steam is being condensed down into condensate. This is not called a condenser. It's called a feed water heater. This would be the way your sketch would be drawn. And let's see. Oh, what we do. So in power plants, what we have a little dilemma on what do we do with the saturated liquid condensate. And at a later time, and probably at more an advanced level, there's one option. You can either pump this condensate up ahead to the feed water pump, or you can let this saturated liquid flow back to the condenser or the open feed water heater. So those are just details that are computational details, hard to pull off, and you will not be expected to do anything like this in this class. So the advantages of the closed feed water heater, relatively simple to implement, okay, with stock heat exchangers that you can order off the shelf, okay. Advantage is that it raises the feed water pump inlet enthalpy, and therefore it's going to reduce the early boiler heating load across a finite delta T. So a closed feed water heater will raise the thermal efficiency of a power plant. The disadvantages, it requires extraction steam from the turbine, okay? And then also dealing with that, the condensate coming out of from the heating steam. You have to decide how are you going to handle that. You can't just send it to drain. It's either got to be pumped ahead or cascaded back to a lower pressure. Okay, that covers regeneration. I want to give you a quick look at reheating of the steam. This is a classic look at the way steam is reheated after it goes through the first stage, early stages, let's say through the high pressure section of a steam turbine. You're going to coming in at superheated vapor. You're going to be leaving probably at superheated vapor, but at a lower temperature. And the steam comes back to the boiler, okay, into what's called a reheater section. Oh, remember the steam drum? If you watch previous video, there's a steam drum where the feed water is turned into saturated vapor. Saturated vapor comes out to a new section called the superheated section. I didn't say that before it goes into the turbine, okay? Out of the turbine at a lower temperature than T4, back to the boiler where it is reheated, returns to the medium or low pressure steam turbine section to state 6, and then out it goes to the condenser. So this is a classic example of steam reheating, and this is what a horizontal reheater would look like. So it's just a bunch of tubes connected to a manifold. That's all that looks like. It's fairly simple to understand, a little tough to implement in the real world because of very, very high temperature operations here. Okay, so that's called steam reheating. Why do we do that? We do that in order to reduce the irreversible heat transfer across a finite delta T, and that will improve the plant thermal efficiency. Advantages, I think it's what I just said. It results in increased turbine power output, therefore increased thermal efficiency. Disadvantages, requires multi-stages of the steam turbine, all connected to the same shaft, and it requires a separate reheater section in the boiler. So this is not something you add on after you've built your power plant. This is something you build into your power plant. Another type of improving thermal efficiency, in other words, reducing the heating load or getting the most you can out of the fuel, air, exhaust mixture, is waste heat recovery. And this is a classic example of a waste heat recovery in a power plant called an economizer. So the economizer is also a basic heat exchanger, and we call this a cross-flow heat exchanger. And so what we've got over here in the picture is we've got hot exhaust gas coming from the boiler furnace section, but it's going to the atmosphere. Here's the exhaust gas going to the boiler stack, okay? And what we're doing is we've got this heat exchanger where we've got water going inside these hairpin tubes, and the feed water is picking up energy by way of heat transfer from the exhaust gas into the feed water. And so this little image here sort of gives you an idea of why we call it a cross-flow heat exchanger. Hot exhaust gas going across these tubes, and inside the tubes is boiler feed water. And you say, well, what would that look like within the boiler? Remember, here's our TH. Here is our high temperature heat source. We're generating steam with that high temperature heat source. But once it makes the turn past these superheaters and reheaters, it's coming down, and we put an economizer in this area just before the exhaust gas goes out to the exhaust stack, okay, the big tall stack, and we recover heat using the economizer. And so this would be state 4 coming into your boiler, and this would be state 1 coming out, going to the steam turbine. Okay, advantages. This is like free energy. This is just energy that you're recovering from the exhaust gas, and it's not costing you a dime other than the capital cost of putting in your economizer. It can dramatically reduce the boiler heat input rate required to boil the water from compressed liquid up to saturated liquid. Disadvantages is it reduces exhaust gas temperature and might cause condensation of water vapor in the exhaust, which could cause corrosion. So operationally, we have to be careful to not pull too much energy out of the exhaust gas such that H2O vapor, a natural exhaust product, right? H2O is a natural exhaust product of any hydrocarbon fuel. We don't want to condense that vapor out of the mixture before sending it up to the surroundings. Closing up heat rejection in the condenser section. Closing up heat rejection delta T. So remember what the condenser looks like. We're condensing from state 2 to state 3, and we're using cooling water, let's say from the river, to accomplish that, Q dot L, into the river water. Recall that the condenser is operating at a low pressure, let's say, for example, 20 degrees C. And so the closer we can get the condensing temperature, the closer we can get it to the river water temperature or the cooling water temperature, the less irreversible our process is going to be. And so recognize, I've given some numbers, for example. So in the SI units, you're looking at typical operation of the condenser is 1.8 to 4 kPa. So I've tabulated these pressures from 15 degrees C up to, let's say, 28 degrees C. So that would be a reasonable range of cooling water. So recognize that we're operating way low pressure, high vacuum, way below atmospheric pressure. And so similarly, in English system of units, typically we operate at pressures that range somewhere between 0.18 and a half of PSI absolute. And for those of you that have some experience, you say, well, what's that in inches of mercury absolute? So that's going to be somewhere between 0.1 inches of mercury absolute, that's near total vacuum, up to 1 inch of mercury. That's pretty easily achievable. Okay, so those are just some areas of comparison where we're trying to close up the temperature difference between the condensing temperature in the condenser and the river water or cooling water temperature. Advantages of this, of closing up the temperature difference in the condenser, it results, the lower pressure you can run, the more power you can get out of your turbine, okay? The disadvantage is that the low temperature heat source is going to be seasonal, right? So operationally, you're going to find you're going to get much better thermal efficiency in the wintertime than you do in the summertime. In the summertime, TL is going to be higher than the wintertime. And let's see, and increasing your condenser vacuum, the lower you run your condenser vacuum, the more air in leakage you're going to have in those flanged connections. And so that's, in some ways, that's a good problem to have. You don't want air in leakage, but you want to get as much power out of your turbine as possible. And you want to decrease the heat transfer across a finite temperature difference. A really neat thing about the Virginia Tech power plant and the Virginia Tech community is the way the power plant utilizes its fuel source. And nowadays, that's mostly natural gas. Fuel source for the Virginia Tech power plant is mostly natural gas. And we call this cogeneration. And so what we do, so in the traditional steam power plant, what do? Traditional steam power plant takes in fuel and it produces net power. And if you run through, look at this percentage. You see how that is pretty much, that's kind of like a thermal efficiency that you could get from a really good Rankine cycle. And so in terms of fuel, 40% of that energy is going into electric power and 60% of it is a loss, right? Okay, so that's kind of bad news. For Virginia Tech, it's really cool. In the wintertime, where Virginia Tech needs a lot of heating, let's see what we do. We're going to take in that same 100% of fuel. We're going to make that same 40% of power from our really good Rankine cycle, okay? But we're going to use 52% of this 100% fuel in terms of heating. We're going to take that steam. We're going to take steam from the exhaust of the turbine which is going to be a little different than a traditional Rankine cycle. And we're going to take that steam and we're going to run it through radiators in dormitories, in academic buildings, and we're going to use that for heating in the wintertime. So this is a wonderful model called cogeneration for when you need process heating, which we do at Virginia Tech. The process is keeping us warm. And so it's a wonderful use of energy in the wintertime, cogeneration. Okay, great idea. And another great idea to go look at your Virginia Tech power plant. Now, there is a little subtle point here. Is that in the wintertime, where Virginia Tech wants that heating steam, you recognize that coming out of the turbine, it has to be pretty hot steam, doesn't it? And so it turns out that your pressure is not going to be down at the condenser pressure. It's going to be at a higher pressure. It's going to be a pressure higher than 1 atmosphere. And so one thing I've shown on this slide is you've got the same TH, but do recognize that P2 for cogeneration, this low pressure here, is going to be a much higher value than the pressure for the Rankine cycle. And so do recognize that typically at Virginia Tech, we're coming out of the turbine at, let's say, 30 PSI gauge, because that 30 PSI gauge is needed to get the steam delivered to all our academic buildings, to all the dormitories for the heating. And that's where that steam is condensed, and then it flows back to the power plant. And so that's an important key thing to remember, is that lower pressure coming out of the turbine is going to be a higher value than your traditional Rankine cycle subatmospheric pressure. This is an image of where I used to work. Okay, it's one of the many big pieces of equipment that we had at our paperboard manufacturing facility in Covington, Virginia. And this is a cogeneration plant in which you can see our fuel. Our fuel is chipped wood, bark, also known as biomass, okay, and sawdust, okay, that we purchase from sawmills at a very, very low cost. And so much of our fuel is nearly free. That's good news, right? And so we take this fuel that's nearly free and we produce electric power to send to the grid and also for our own manufacturing needs. And we use the process steam that comes out of the turbine for our manufacturing needs, which is a significant amount of heating. And we use that in the paper manufacturing process. So this is a tremendous value to the company now known as Smurfit Westrock. Let's see. Let me look at my title. It says to cogeneration or not. This cogeneration decision has to be made at the design point. It's not made overnight or over a weekend. So this cogeneration decision has got to be a new installation project, and it strongly depends on financial analysis. And so do, as an engineer, recognize that the cost to operate is driven by electric power requirements and heating requirements. The combination of those requires a lot of study, and the value of this has got to be played off with the capital cost to install the equipment. So just to recap, it's all about minimizing the cost to operate, and also in this case, minimizing the capital cost to install the equipment to accomplish what you're trying to accomplish. You get the same idea about advantages and disadvantages. Huge opportunity for nearly full utilization of your high temperature heat source. Okay, so that covered a lot of slides, but what that does is serve you, hopefully, to suggest to you, go have a look at the Virginia Tech power plant if you have the opportunity to do so on a tour. Also, then backing up, I wanted to give you an intro to regeneration to give you an idea of why are these mean instructors assigning you these very difficult power plant analysis problems in this class. Well, the reason is to improve the thermal efficiency of a basic Rankine cycle power plant. Okay. Hope that helps. Hope you got some information from this and also some appreciation of why we're asking you to do what we're asking.